Hey guys, I wanted to put together a quick video for you guys to help kind of filter through some of this material for the urinary system in an effort to keep them short and sweet so you don't have to listen to me for long periods of time. I'll probably post a couple short videos over the next couple of days that focus on different parts of the urinary system. Make sure you're going through the PowerPoints and looking at each slide, particularly the tissue types and the layers and all that good stuff. But for this particular video, I want to focus on just an overview, what the urinary system is doing and how we're actually going through those 3 steps of urine formation. I'm going to use a couple of crazy analogies because I know that'll help give you guys sort of a visual of what's happening, and they're ones that teachers like to use a lot. So you guys, urinary system. We've been talking about how the respiratory system fills that blood with oxygen to take it to our cells. We just finished up the digestive system, how we fuel those cells with glucose and other main macromolecules. We secreted waste, essentially our feces, you guys, but that was what was left over as insoluble or indigestible materials from our digestive system. But remember, that's just a tube, right? We're glorified donuts. We have an opening and an exit. But what do we do with all of the things that kind of distribute throughout our body that we don't use? What do we do with all of those waste materials that end up in our intercellular fluid, within the cells? How do we get rid of those? Because we can't really eliminate them in our wastes. This is where your urinary system comes into play. So the first analogy that teachers like to use a lot is cleaning out your fridge. And I'll post a great crash course video that helps illustrate this a little bit. You guys, when you go to clean out your fridge, you don't just pick out a few things and then leave it as it is. You take everything out of your fridge, wipe the fridge down, throw away the bad stuff, but you don't want to throw away the expensive stuff that hasn't expired yet. You want to put the good stuff back in the fridge. Think about that when you think about urine formation. What are we cleaning out? The blood. We're going to take everything out. We're going to put the bad stuff through this filtrate system and eliminate it from our body as urine. And we're going to put the good stuff back, the stuff that we can use again, some proteins, some electrolytes, some things that we can kind of recycle through our body. This whole process of cleaning out the blood is how we make urine, and that's going to be critical. It's the blood that we're actually cleaning out. So it's going to help with a couple of our other major systems, particularly what was that system that helped us breathe in and breathe out some of the oxygen and carbon dioxide waste? Awkward pause for the respiratory system. And then the cardiovascular system, right? Heart to lungs to heart to body. We're going to have to work hand in hand with those systems to help get this taken care of. Now, in the cardiovascular system, where did a lot of that exchange take place? What's the smallest layer of our vessels? That's right, capillaries. So you can assume that capillaries are going to be a place where a lot of this exchange is going to be happening. So I'm going to go to one particular slide from your PowerPoint presentation. So I'm going to share that with you guys now. The path of filtrate through the nephron. You guys, on your own time, go ahead and look at the major players of the urinary system, right? The 2 kidneys, the adrenal glands. Your ureters are the tubes that lead from the kidneys to the urinary bladder. Your urethra is what's going to lead from the urinary bladder to the outside of the body. There's a couple fun facts in there, like the male urethra is much longer, therefore less prone to bacterial infections. In females, it's much shorter, so we have more complications with infections and UTIs and things like that. So urethra is how we get outside of the body. You guys, are just layers and layers and layers. I'd always tell you guys, it's all about the layers. Your kidneys are going to have a couple different layers. Particularly, they're going to have that kind of medulla and then the cortex, the outside and the inside. It's very much like your adrenal glands. The outside is going to be a little bit thicker. The inside is going to be a little bit more gilly. It's going to look like an upside down mushroom, right? All the gills of a mushroom, just like your adrenal glands. There's going to be very specific things happening in each one of these levels too. So we're going to go through that in a little more detail. You guys, another fun thing to keep in mind is your kidneys are also retroperitoneal. Remember that big old Ziploc bag that held together all of your intestinal gutses, that was your peritoneum. And we're gonna focus a lot for this next midterm on what part attaches to the actual organs, visceral, what part attaches to the actual walls of your body, parietal peritoneum. But your kidneys are going to sit retro or behind. So they're not going to lie within that actual peritoneum. So they have very specific layers that help anchor them and insulate them. Fatty layers for insulation, lots of very structurally supportive layers to help keep them in that floating position. So they sit more towards your backside and away from that peritoneum. Now, we said that urine formation was pulling things out of the blood and putting it back in. The functional unit of your urinary system is the nephron. The nephron is where this is happening. And I'm going to use a few new analogies for you guys. But just think about it. What was the functional unit of your respiratory system? Functional unit means where is the work actually happening? Your alveoli, right? That's where the actual exchange was taking place. The smallest capillary level, the alveoli. Here, it's going to be taking place in your nephron. And there are hundreds and thousands of nephrons within each kidney, you guys. So there's a lot of surface area to take care of this. When you're looking at this slide, slide 20, I'm going to talk about this one a little bit. You're going to see that we've got this red kind of ball, the glomerulus. The glomerulus is going to be a ball of capillaries. So that ball of capillaries, glomerulus in Latin really does mean ball of yarn. That's going to be a capillary bed. And the reason we have so much ability to do more filtration here than normal blood capillaries is because they are all wound up like this in this tight little knot. Now, the glomerular capsule or Bowman's capsule is going to be what surrounds that. You still have your afferent arteriole that leads in and your efferent that leads out. Because remember, we're going to clean it out. We're going to take stuff out and then send it on this tube slide to make urine. But we're going to put good stuff back in and continue sending it on its way through the rest of the cells in our body. So here's where our next analogy is going to come into play. A water park. I like to think of the nephron as a giant water park, you guys, and you'll see a lot of videos. I'll post some more short videos that kind of illustrate this for you. So imagine, right, you're going on this urine water park slide. So you're going to climb your afferent arteriole, that's the ladder to get all the way to the top of the slide, and you're going to enter that glomerulus, the glomerular capsule. Imagine this as being the platform where you've got that lifeguard that's stopping you before you can go down the slide. You've got to wait until everyone else goes down. You've got to wait until it's your turn. So that glomerular capsule is where the lifeguard's kind of waiting and making you pause. This is where you're going to either go down the slide or turn around and go back onto that arteriole to the rest of the body. Now, once you go down that slide, we've got the proximal convoluted tubule. Proximal means closer to. You've got the loop of Henle. So imagine on your water slide, this is where it just drops, right? Your stomach comes up, you feel that drop, you're going to drop down that loop of Henle that dips into your renal medulla. Then you're going to have your distal convoluted tubule. Convoluted means just twisted, right? Distal is further away. So this is going to be a little bit further away. By the time you get to this end of the slide, you're pretty much almost at that urine point. You've been filtered out. We're going to pull some things on and off of that slide. Once you get to the end of the slide, now you're ready to get off, go down the collecting duct and into that kind of minor calyx and become the urine. So that collecting duct is going to be how they filter everyone off of the slides to go get back in line or exit the body through the urinary bladder and the urethra. So that's the major idea, right? This water park slide. So here are a few things I want you to think about. Number one, look at all the capillaries intertwined in that nephron. The nephron's everything in yellow: the glomerulus, the glomerular capsule, the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule. But the capillary beds are intertwined in there, and that's important because the 3 steps of urine formation are glomerular filtration, tubular secretion, and tubular reabsorption. So you're going to climb up that water park slide, that arteriole. You're going to go into the glomerulus. That's going to be glomerular filtration. This is where the force of the blood against the walls of those capillaries is going to push that blood through. It's going to push, it's going to act essentially like a sieve, right? You guys, it's going to be like a colander. You're going to pour all that blood through a colander. All the big bulky stuff like red blood cells, a lot of your proteins, those are going to continue on. They're going to keep going through that efferent arteriole back out into the world. But the wastes and the things that are bad are going to kind of accumulate and get in line to ride down that proximal convoluted tubule. So glomerular filtration, step one. Walk up the ladder, get in the glomerulus, and then get decided if you're going to go down that slide or not. Now, another key thing to think about, you guys, is what could be a cause and effect of that force of blood. High blood pressure, low blood pressure, blood volume, all of these things will affect the ride you're going to take down that slide. Think about it. If you got up to a water park slide and the water wasn't shooting out, there was not a really heavy stream of water, what's going to happen when you go down that slide? Skirt, you're going to feel your butt cheeks kind of drag all the way down that slide because you don't have enough water force to make it go through that slide. This would be a low blood pressure situation, you guys. If there's low blood pressure, there's not a lot of water on your water park slide, and it makes it harder to make that urine formation happen. In contrast, what if you get to a water park slide, your glomerulus, and the blood pressure is very, very high, abnormally high? Well, then you've got water shooting into that slide. What's going to happen when you sit down? It's going to push you through too quickly, or it's going to shoot you right off of the side, right? So high blood pressure would be a problem as well because you're not actually filtering it the way you need to filter it. You have to have a perfect combination of blood pressure and blood volume to make that happen, to make that urine formation possible. So that's a lot of what dictates how much urine is created and formed. That blood pressure and blood volume, that force of the blood against the walls of the arteries and capillaries is what's going to push the blood through that filtration. Okay, so you made it to the top of the water park slide. Conditions are just right. Now you're going to head down that proximal convoluted tubule. You guys, once you start going through that proximal convoluted tubule, you're still essentially in that kind of renal cortex area. Once you dip down into that loop of Henle, down into the renal medulla, a lot of things are happening. This is going to be tubular secretion. Tubular secretion is where we're still pulling things out of it, right? Just because you filtered in that glomerular capsule, we're still going to have things kind of leaking in and out of the pores of this tube system. And we'll hear a lot of words as you go through your slides, a lot of those same porous words that we've talked about in a lot of our arteries. There's a lot of pores, there's a lot of openings so that the right materials can pull out and then pull in. There's going to be a lot of pushing and pulling going on, especially with a lot of our ions like sodium and potassium and chlorides. You guys, the one thing to keep in mind is salt sucks. Remember that. Salt sucks. It's your basic definition of osmosis. Osmosis moves from areas of high water concentration to low water concentration, but typically that also means that wherever there's a high solute concentration, like salt, there's not a lot of water happening. I'll post some more videos on this, but I want to stick today just to a short urine formation video. You guys, there's going to be accumulations of sodium on either side of that loop of Henle. And the whole point is to either pull water into the water slide or pull water out of it, depending on the level of hydration of your body. This can cause problems if you have a high sodium diet. If there's too much salt in that extracellular area, kind of around the renal medulla and around that loop of Henle, what's it going to do to your water park slide? Salt does what? Suck. Salt is going to pull the water out of that loop of Henle and make it harder to create that urine because you're depending on that urine formation to keep moving through that nephron. So if you have a lot of sodium, a lot of salt in that extra area outside of the loop of Henle, it's going to pull too much water from that urine formation and create a dehydration situation. If you don't have enough of that salt on the outside, it's not going to pull enough water out and you're going to end up flushing too frequently. There is such a thing as being overly hydrated. We need to have that perfect balance. I'm doing that seesaw thing with my arm right now, right? You guys, what's that perfect balance within the body? Homeostasis. So your urine formation, that tubular secretion, what we're trying to do is pull out some of the things that we still might be able to use, have a perfect combination of salt and water, and we're depending on that to kind of create that urine balance. Now, once we go through the loop of Henle, where our tubular secretion and reabsorption is starting, we get to the distal convoluted tubule. Once we get to this point on our water park slide, you guys, we're pretty much urine. At this point, we have the perfect balance. We've gotten rid of everything that's useful and put it back into our system. All that's left is our waste product. And when we talk about waste product in urine, you guys, this is urea, all of the side products that come from our macromolecules, right? When you break down proteins, when you break down lipids, when you break down carbohydrates and nucleic acids, you end up with byproducts. And urea is a major byproduct. It's one of the major byproducts of urine. We also have some small amounts of other things, but for the most part, it's going to be waste products like urea, and 90% of it's going to be a lot of water as well to help flush that out. So once you've made it to the distal convoluted tubule, we've done all parts, right? Glomerular filtration, tubular secretion, and tubular reabsorption. And once we get to the collecting duct, we are finally urine. So I'll give another video in just a few minutes about a lot of the ions that we're talking about. And remember, ions are charged particles. So you have to think back to basic chemistry and biology, your periodic table. They can be cations, which are positively charged, or anions, which are negatively charged. But you guys, these are just particles that are in our body that we need to kind of depend on to help that balance of tubular secretion and tubular reabsorption. So I'll do a separate video for that. But this today was just to help give us an overview, right? We're taking everything out of the blood. We're putting back the good to continue its journey through our cardiovascular system, eventually to our lungs, because again, the lungs help kind of secrete some of that CO2, which is a byproduct. And then we're also going to go through three main steps: glomerular filtration, tubular secretion, and tubular reabsorption. That's when you think about your water park slide, you guys. The force of the blood is like the water pushing you through that slide, and that's a very delicate balance. In the end, we end up with urine that can tell us a lot about our body. We can see that if urine has white blood cells in it, that typically means that there's an infection, right? There are certain things that should never be in your urine, you guys. We're supposed to put the good stuff back. So we've been using urine as a way to diagnose and treat patients as before there were even physicians, right? And they were doing crazy things like tasting the urine to see if it tasted salty or sweet. If there was glucose in the urine, that meant that there was a problem and we were secreting some of that glucose before our cells had a chance to get it. When we were just talking about our digestive system, cloudy urine typically meant white blood cells, which would be an infection. Any sort of pink or blood in the urine, we were able to tell a lot from that urine formation. So this quick video was just to go over those three steps of urine formation. I'll post a few more to kind of help with some of those key ion components, but you guys make sure you go through your layers, and if you have any questions, check out some of the video animations that I'll post a little bit later. That's it for now. Have a good rest of your day.